Hi guys, welcome to the new episode. In this episode I am going to talk about the remaining details of marginal rate of substitution and sort of the technical details of how we calculate it. Alright, so we start with a simple example with utility function having two variables, x and y. Alright, so x and y are both real numbers. Alright, plus, and so utility function is basically from r squared plus into r. Alright, so I will first talk about what we call total derivative. Alright, total derivative. So what is the idea? Idea is the following. If you make a change, so if your function is one parameter, alright, if you make a change in the parameter, how much change is going to happen to the function is calculated by the derivative of this function, right? Incremental increase in the or decrease in the parameter leads to some change in the function itself, and so this is what's called the slope of the function and or the derivative of the function. So the same idea, the derivative, but if we have two variables. So when we change the both parameter, not just one, but both parameters, well, how much this change is going to change the level of the function. All right, so here I have the utility function, and let's suppose this is equal to z, right? So z is the third dimension. So given x and y, z is the height of my utility function, or this is the utility level. All right, so what I want to do, I want to calculate not the new level of z once I change x and y, but instead I would like to calculate the change in z. How much change in z is, how much change in the level of utility, the interpretation, will occur if I change x and y in a very tiny amount. So that should be, all right, x plus dx and y plus dy. Minus xy. All right, so this is a definition, by the way. All right, so this is how we define the total derivative. So some definitions may not come to you 100% natural, but in fact it is, I think, quite intuitive. Well, why is that? Well, remember, I want to understand the level of utility level change because of the change in x and y, and so that should be my initial condition, my final condition minus the initial condition, so that should sum up the change in the utility level, right? So at the end, another point that I want to make is that this dx and dy do not have to be positive, so this x plus dx, all right, or x minus dx, no difference at all, because dx can be positive or negative, same for the dy. All right, well, how do we approximate this, right? Because if my utility function is continuous, if the domain is something like r squared, dz, what is dz? Well, a unit of change, but yeah, what is the smallest unit of change in a continuous parameter value? Well, so therefore we approximate it. How? Well, we basically do it as follows. So dz should be, remember, this change is nothing but the partial derivative of the u function with respect to x times dx plus partial derivative of u with respect to y times dy. Well, why is that so? Well, because this is, amount of change in x, but in the x direction, and amount of change in y in the y direction. All right, so therefore this total sum has to be equal to the change in the z. So that's again the definition of total derivative. So what we are going to do, we are going to apply this to my utility function and find the marginal rate of substitution. So let's revisit the idea of marginal rate of substitution. Well, the idea was that there are two situations. Situation one, initial situation. Situation two, some changes. I decrease my consumption in one good, and then I should probably increase my consumption in the second good if the utility function is increasing. And so I want to know, what rate how much additional banana I should consume for 1 unit of apple I gave up. So, but the idea was to keep my utility level in both in the initial situation and the final situation same, remember? So that means these 2 points must be on the same indifference curve. Well, this is sort of an exaggerated graph, all right? Because I want to make changes very, very small, not just 1 unit or 2 units, but very small, like 0.00001, etc. So this is, let's call xy, all right? And this is the x plus, x plus dx, y plus dy. Well, I mean, again, don't be confused that dx may be negative, all right? And here dy is positive, all right? So this positive should not confuse you. All right, so I was here, I want to come back here, so, what is the rate of change? Well, the idea is basically the following, right? So I create this triangle here. So the change in here on the y-axis is just dy unit, and the change in this direction is just dx unit. So therefore, coming from this point to sort of remember we want to find the slope of the function. So that means you pick 2 points and then, draw a triangle and find the sort of the tangency of this angle, which is nothing but dy over dx. But don't forget, this dy and dx are actually very, very small. So therefore, as dx and dy approaches 0, this dotted line is basically going to come to a perfect tangency at some point. And so it is actually going to, in the limit, going to give me the slope of the tangency line at that point, all right? Obviously, xy will also move with that point as well. So that means, let's start a new line. I need to start with my utility function equals to some c, where c is a real number. So this is my indifference curve. Remember, I want both the initial point and the final point on the same indifference curve. Very good. So change in z because of the change in x and y. Well, change in x and y is just del u del x, all right? Calculated xy point, obviously, times dx plus del u del y, again calculated at xy point, times dy. So this is time. So equals to change in c. Well, remember, I don't want to change the level of utility. I want these 2 points to be indifferent. So therefore, change in c must be 0. So dz in this new framework is just 0. So how do I calculate dy over dx? That's my purpose. Well, simple. Just leave dy here, send the dx term to the other side. So I'm going to skip this xy parentheses thing because it makes the notation long. So I have du dy times dy equals minus del u del x dx. So divide both sides by dx. Assuming that dx is non-zero, and then divide both sides by del u del y. Del u del y. Again, assuming that del u del y, the marginal derivative, partial derivative, or the marginal utility is non-zero. So once I do that, these are going to cancel out, and dx will cancel out, assuming that they're non-zero. So what I'm left with is dy over dx, all right? So the rate of change between good x and good y is nothing but minus del u del x divided by del u del y, all right? So if you remember, so that's something probably more that you're familiar with from the intermediate micro courses. This is nothing but marginal utility of good x and marginal utility of good y, and don't forget the minus sign. And if you remember, this is nothing but marginal rate of substitution. So in fact, the marginal rate of substitution is just dy over dx, and so therefore it's equal to minus of marginal utility of good x divided by marginal utility of good y. So this is how we calculate MRS of a utility function at any given point. So don't forget, here the marginal utility of good x depends on the point, the initial point. If you change the initial point somewhere here, clearly the slope will change. So that means MRS will change as well. So all these arguments you probably are familiar from intermediate micro. Okay, so basically that's it if we have two variables. But what if I have a function, a utility function, with more than two variables? Can I really make the same arguments? Exactly, you can. I mean, the total derivative does not just work for utility functions with two variables. So let's suppose my utility function is from Rn plus into R, all right? So therefore, when I talk about, an alternative, I in fact mean a vector with n dimension. So therefore, I can still derive the marginal rate of substitution. I'm going to call it, for example, well, instead of 1, 2, I can just call it ij. So the marginal rate of substitution between good I and good j. So this is minus del u, del I, divided by del u, del j. All right. So as simple as this. So this is the marginal rate of substitution between any two goods, and where I and j are basically coming from 1 all the way to n. Okay. And obviously I am assuming that I and j are different. Okay, because otherwise the marginal rate of substitution between good I and good I is like 1 minus 1, but conceptually that means something crazy. The rate of substitution, well, you substitute one good with another, so you don't substitute the good with itself. So therefore I and j should be different. So even if I have different variables, n variables, I can calculate the MRS. Usually we assume, along with many other things like the utility function should be increasing, etc., etc., is again, increasing utility function is just a simplification assumption, a technical simplification assumption. But sort of an important assumption is what we call diminishing marginal utility. All right. That means if you have just one parameter, or maybe more than one parameter, so your marginal utility with respect to that parameter xi is negative, maybe 0, but it's not positive. All right. Which means the more you consume, yes, you get happier. All right. So be careful about that. The level of utility increases because u is assumed that u is an increasing function. However, the amount of increase at every additional unit of xi you consume is not going to be increasing. All right, it's going to be sort of you're going to get saturated. It's like eating a beautiful chocolate cake. All right, there's like, let's say, a huge chocolate cake in front of you. You start eating. Initially, assume that you love chocolate cake. I do. So initially, with the first bite, you get incredible pleasure, and then the second bite, exactly, same amount of pleasure. The third, fourth, fifth. Well, then the sixth bite. Well, I mean, yes, it is still nice, good, but it's not as good as the first one. You see what I mean? And then the 15th bite, if you have the stomach for it and the fitness for it, the 15th or the 16th, you see what I mean? As you increase the amount of consumption, well, you will probably get happier. Well, but the amount of additional happiness you get out of this additional unit of consumption is not going to be as high as the first bite or the second bite. That's the idea of diminishing marginal utility. All right. And similarly, the marginal rate of substitution also follows a similar line. So the marginal rate of substitution, don't forget this. So the marginal rate of substitution is nothing but slope of indifference curves. All right. If you do not understand any of the technicalities here, this is at least one point that you should sort of get. Marginal rate of substitution is nothing but the slope of the indifference curves of a given utility function. And as we draw it in this line, the slope is basically decreasing, right? Slope here is almost like, the angle here of this triangle is almost like 90 degrees, and then it's decreasing, and here it's almost like tangent to the x-axis, like 0. So the slope is decreasing basically. So therefore the absolute value of marginal rate of substitution is decreasing. So what does that mean? That means when, for example, I am consuming huge amount of x, all right, in order to keep myself very happy, so that means I am consuming very little y. So if I slightly want to increase my y consumption, I have to give up a lot of x's, all right? Or put differently, if I want to decrease y a little bit, you have to give me a lot of x's, all right? So the rate of substitution is increasing. And here the rate of substitution is increasing in the dimension that for one small y you have to give me a lot of x's, and here for one small y you have to give me very, very small x. All right, so in that sense it is decreasing, and here it is increasing. And this sort of diminishing return is basically due to the assumption that preferences are convex. All right, that's also one of the implicit assumption that we make. Again, these are assumptions, right? They are not facts of the reality, but these assumptions in many frameworks are good because in many environments, the individual's preferences do actually seem as if they are maximizing a convex preferences, or at least sort of it's an intuitive and reasonable assumption in some environments. So what does it mean that preferences are convex? Okay, so let's define this more formally. Convex preferences. All right. So a preference relation on X is convex if the at least as good as set for any A in X is a convex set, as easy as this. All right, so what does that mean? That means, oh, by the way, if we don't know the preference relation, but we know the utility function that represents this preference relation, well, then we say that still preferences are convex if for any A in X, the at least as good as set of this point A. Remember how we define this is like X in X such that U of X greater than or equal to U of A. All right, this set is convex. All right, the same idea. If you don't know the preferences but you know the utility function, well, then you look at this at least as good as set definition. But what does that mean? So if you draw the indifference curve of any point, again, let's assume that we are in R square plus. So if you take a point A and draw the indifference curve, so let's suppose this is the indifference curve, well, the at least as good as set is, everything above and on this indifference curve, right? And this set, well, it goes all the way here, so like up to infinity. Oh, of course, it never touches to the horizontal axis. So it's just exaggerated a bit. So this set is clearly convex. At least visually, it's obvious to show that it is convex. Another example, I'm just drawing the indifference curves randomly. Later, we are going to talk about specific utility functions and their specific indifference curves, and you will see not all of them are convex. So one indifference curve, given that A is here, would be like this. So the at least as good as set can be this area, all right? So above this curve and on this curve. And clearly this set is not convex, because if you, for example, take A here, B here, and draw the convex combination, please go back to the math review section and review what we meant by convex sets. So if you draw a convex combination, a straight line between these any 2 points A, B like this, some of the points are going to be outside of this at least as good as set. So therefore that means the at least as good as set is not convex for this utility function or preference relation, and hence this preference relation is not convex. So one question, a reasonable and good question, is that why we need this assumption, or what does it really bring, or what does it really teach us? Well, simple. A convex preference is going to have this sort of indifference curves bowed in, all right? And it means if you pick, for example, this point and this point, all right, A here and B here, this guy is indifferent between A and B, and you look at a convex combination, for example, this point, 1/2 A, 1/2 B, all right? So what does that mean? That means, for example, here I am consuming 2 apples, 5 apples and 2 bananas, and here I'm consuming 2 apples, 5 bananas, all right? Well, I wish I would pick something more divisible by 2. So it's a 4 to 2, let's make it 4 to 2, and so therefore this is 2 to 4. So 2 apples, 4 banana, 4 apples, 2 bananas. And then this midpoint is basically 1/2 of A, right? I'm sorry. Yeah, 1/2 of A, which means, 1/2 of 4, 2 plus 1/2 of 2, 4. So that means 1/2 times 4. I'm assuming that you guys already know how to, multiply a vector with a scalar and add 2 vectors from your previous math courses. If you don't, please, I didn't talk about it in the math reviews, but sort of you can just, learn it very quickly. These are just, set of rules that, all the students must know, at least at this level. So this is 1/2 4 plus 1/2 2, comma. So this is what we do in the x component, and the y component, y/2 2 plus 1/2 4, 1/2 4. So basically this is nothing but, 6 over 2. So it's this point is 3 to 3. All right. So this is a convex preference. So what does that mean? And by the way, we know that this 3.3 lies on a higher indifference curve. So that means if your preferences are convex, all right, more balanced bundles are always more preferable. All right, let me note it here. More balanced bundles are more preferable or more preferred. So here, what makes A extreme? Everything is relative, obviously, right? Here we have extreme, quote unquote, extreme amount of good X and extreme amount, and here we have extreme amount of good Y relative to this one. And so this is sort of more balanced between 2 goods. But you may say, well, a point here, for example, is it more balanced? Well, in comparison to this one and this one, like these are like the opposite ends, and so in that sense, all right, it's just an intuition. You don't have to agree with it, but that's the intuition. The more balanced bundles are more preferable if your preferences are convex. If your preferences are not convex, as in this example, you can't really say that. obviously. You know, some points are more preferred, some points are less preferred, right? Because those points are not in the at least as good as interval, so they are worse than set. At least as good as interval, no, there's no such thing. At least as good as set, and those points are therefore at the worse than set. But to me, you know, convexity is a technical assumption. Convex preferences are nice because, you know, convex domains are nice. Convex preferences always gives us smooth surface. So the optimization problems will always be easier to deal with. I mean, that's the technical reason. And so this is just the intuition we make up. You buy it or not. But that's the idea of convexity in preferences. Okay, I hope that was clear.